Historically, traffic safety engineering operated on a grim premise, waiting for catastrophic failures to dictate where improvements were needed. To track systemic failures, engineers relied heavily on post-incident data. Looking at this collision diagram, you can see how past crashes are mapped. By plotting specific vectors of failure onto intersection geometry, engineers built a historical record of trauma. This approach creates a brutal feedback loop. The data requires actual accidents to occur before the geometry is deemed unsafe. To officially classify a location as a black spot, requiring redesign, a statistically significant number of people first have to get hurt or die at that exact location. Relying purely on statistical accident analysis traps the engineer in a reactive posture. Waiting for the data to accumulate is no longer an acceptable standard for modern infrastructure. The modern response is codified here in the Unit 4 syllabus, shifting from post-accident repair to pre-construction prevention. First, the Road Safety Audit eliminates risks in the design phase. Second, strict vehicular emission norms mandate managing the network's environmental impact. Engineers can no longer simply calculate expected traffic volume and lay down pavement. They must navigate these strict, proactive policy gates. These gates function as hard filters. If a proposed design fails the safety audit or violates emissions laws, the project is halted entirely, regardless of its theoretical efficiency. Volume calculations and design speeds are insufficient on their own. A project that optimizes traffic flow but fails at safety audit will never move past the planning stage. The Road Safety Audit is a formal, rigorous examination of the future road project, rather than a cursory check of the plans. This brings us to the RSA team. For the audit to function correctly, this group must be completely independent from the original design team. This strict separation eliminates cognitive bias, ensuring auditors don't share the creator's blind spots, allowing them to objectively reject flawed designs. When examining the elements of the RSA, auditors specifically hunt for human factor errors. They look for inadequate sight distances, confusing signage, and poor horizontal alignments that a designer might have overlooked on paper. This sharply contrasts older methods from the text, which relied on reactionary geometric corrections only after a collision history was established. The direct output of this investigation is the RSA report. Rather than a final grade, this report acts as a living document. It dictates absolute go or no-go decisions at multiple project phases: pre-construction phase, during active construction, and immediately pre-opening. The RSA framework forces engineers out of fixing broken roads, requiring them to manage systemic risk entirely in the theoretical phase. Physical crash safety is only half of the modern compliance equation. We must also consider the environmental mandate. In India, fulfilling raw physical capacity targets has directly correlated to severe ecological and atmospheric degradation, clearly visible in the thick smog obscuring heavy traffic. To combat this, the Motor Vehicle Act is the foundational framework, regulating not just movement, but a vehicle's legal right to exist on the network. This chart demonstrates the technical thresholds of vehicular emission norms in India. You can see the progressive step down from BS4 to BS6 standards, sharply limiting the permissible toxicity of the traffic flow. These strict emission norms tie directly back into the engineering factors that affect fuel consumption, specifically vehicle speed, intersection delay times, and road gradient. Under these norms, an intersection that causes excessive idling due to poor signal phasing carries the same weight as a violation of environmental law. Environmental regulations now act as a hard atmospheric capacity limit, constraining the design just as rigidly as the physical width of the lanes. Theoretical safety audits and clean air mandates hold no weight without rigorous, on-the-ground enforcement. The Motor Vehicle Act empowers authorities to penalize violations. This closes the loop on the 3 E's principle: engineering, enforcement, and education. While enforcement controls human behavior, the engineering discipline must adapt to chemical constraints by integrating alternate fuels into the system. Transitioning the vehicle fleet to CNG, electric, or hybrid models alters the long-term viability of the entire highway network. By adopting these fuels, the atmospheric bottleneck is reduced. This allows the system to process higher traffic capacities without breaching those strict environmental norms. Active enforcement and the adoption of alternative fuels remain the primary tools for maintaining the delicate balance between increasing traffic demand and unyielding ecological limits. Today, modern highways function as heavily regulated socio-technical systems, where raw mechanical design must seamlessly align with overarching administrative policy. We must contrast raw mechanical equations, like skid resistance and volume calculations, with the policy approvals mandated by Unit 4. These elements converge into a single requirement. An engineer cannot accurately determine practical capacity or design safe intersections without adhering to RSA and environmental laws. This unit transforms the 3 E's of safety from theoretical guidelines into a national legal mandate. The RSA forces proactive engineering. The Motor Vehicle Act demands enforcement, and public culture provides necessary education. Mastering this material means transitioning from a technician who merely calculates to a professional who governs infrastructure. The ultimate test is not calculating how many cars can physically fit on a stretch of pavement. The true measure of a civil engineer is ensuring those vehicles travel safely and sustainably within the absolute constraints of modern law.